The universe is still a place of mystery and wonder. As a cosmologist, I'm exhilarated that we can make some progress towards tackling what seem very fundamental questions. These programs focus on, was there a beginning? Whether we are alone? What's the future of the cosmos? What is the nature of reality? With each advance, new questions come into sharper focus. The key issue is what we still don't know.
It's perhaps the oldest question of all. Why are we here? In this vast and complex universe, are we important?
Many people have a fascination with their environment. Not just the immediate environment. It leads you to think about our place in the wider cosmos.
And it's not just a question for philosophers. Science has been tackling the question too, asking whether there is a hidden purpose to our creation. Or are we just an accident of creation? And in trying to find out why we're here, they asked first how we were created. And the question led to a shocking revelation. It seems our creation was far more precarious than anyone had ever imagined. The result of two mysterious but crucial constituents of the universe that until recently had entirely evaded detection. Without them, we could not exist. So what are they? And can they help us to answer the biggest question of them all?
The aim of science is to try and find patterns and regularities in nature. The first success was actually in astronomy because the ancients realized that the planets moved in regular courses, the seasons and the calendar were regular, and they were able to understand these patterns to some extent. It took much longer to achieve any success in subjects other than astronomy because the stars and planets in their courses display far greater regularity than almost anything else we can study in nature.
In trying to understand how we got here, science turned from patterns in the heavens to patterns here on Earth. Was there a common essence from which everything was made? We've always suspected that in some mysterious way we were connected to the world around us. And that despite the apparent complexity of the world, this common essence could be found by reducing everything into its basic parts.
The Greeks did this, and many of them had the idea that everything was made up of four substances: earth, air, fire, and water, in different combinations. That was a marvelous unifying idea. We now realize it didn't explain things in detail.
People have always been asking these big questions, I think, for as long as humans have walked the earth. And the big change is that now we have measurements, we have data. It started out with the chemists realizing that even though there seemed to be thousands of different kinds of stuff, there was only 100 or so different chemical elements out of which you could build everything else.
Despite the complexity of our world, everything including us is built by combining these basic chemical elements, atoms.
The bedrock of 20th century science was to understand that we and everything else are made up of atoms. and to understand those atoms and to actually do experiments so we can learn what the individual atoms are. We now know that there are 92 different kinds of atoms which occur naturally. The same atoms combined together in different ways make up everything. Every substance is a particular combination of atoms in particular proportions.
Atoms are the building blocks, the fundamental essence of everything on Earth. The difference between complex and simple structures depends on how many different kinds of atoms are combined. A single crystal of salt contains only 2 of the 92 elements, sodium and chlorine.
To build a crystal, you just keep piling on these atoms in exactly the same way, repeating all over again, making it ultimately very, very simple to describe.
A crystal is an example of something which is not particularly complicated. But most things, most interesting things in nature, don't have such a simple recipe.
The big difference between, on one hand, a dead thing like a crystal, and on the other hand, a living thing, isn't what they're made of, because they're both made of the same building blocks, the same kind of atoms. It's rather the complexity in how they're put together.
That's certainly the case of the simplest organisms. An ant, for instance. If you were to peel away layer after layer, you'd get interesting structure on all scales, all the way down to the single atoms.
An ant's body is made of cells, which make up everything from its eyes to its legs. Each of these cells is made up of molecules like proteins and DNA, long chains of different atoms bound together. Yet this unique creature is made of the same atoms that can be found everywhere on Earth.
To get something really complicated, there must be very large numbers of atoms put together.
If you want to build a squirrel, even to build one cell of the squirrel, one chromosome, you have to take these atoms and keep putting them in new and different ways without repeating yourself. And that's how you get this fantastic complexity, which is to me really the hallmark of life.
That's what makes the living world complicated compared to a crystal.
And the most complicated object that nature has ever constructed out of atoms is us.
We can say with some confidence that human beings are the most complicated things in the universe. We're certainly the most complicated things we know about. Human beings contain 10,000 trillion atoms, linked together in a very complicated way. But the important thing about us is not that we're made up of these atoms, but the way those atoms are combined, which determines the complexity of life.
From just 92 atoms, everything on Earth is constructed. Billions of different combinations, creating everything we can see. From the simplest, a salt crystal, to living things, and the most complex living thing, us. But how did atoms ever combine to create us?
To get a complex universe built out of Lego, or atoms as our fundamental building blocks, you basically need only 2 things. You need lots of Lego, and you need lots of space and time to play with them. A key property of the atoms is that they can combine with others and make these complicated molecules. And that's a property that they've always had, ever since the beginning. The rest is just limited by the imagination of nature and doing clever architecture with them.
And since the beginning, every atom on Earth has remained unchanged. But they have been endlessly combining in different ways, joining and rejoining, passing through different substances, living and inanimate. And the pinnacle of this process is us.
It's taken nature about 4 billion years to get from the simplest life in the primordial Earth to us. We don't quite know how that happened. We just don't know. The mix of atoms here on Earth now, carbon, oxygen and the rest, is the same as it was when the Earth formed 4.5 billion years ago. Because atoms can't be created or destroyed by any process we know about that's going on here on Earth. Those atoms must therefore have been produced somewhere, somehow, before our solar system formed.
So to truly figure out our origins, to understand how, and perhaps why nature created us, we have to discover where the 92 elements that formed the Earth came from. In trying to discover if there might be a reason for our existence, scientists had found everything is built from the same 92 elements that have been present on Earth since its creation.
If you want to know where the atoms we are made of come from, the answer leads us back before the solar system was formed, towards thinking about the entire cosmos and everything that happened since the very beginning of our entire universe.
Early on, people thought that what was up in the heavens had nothing to do with us. They didn't even think that the same laws of physics apply to the heavens as to us. This idea is very deeply entrenched in much Greek philosophy, for example, that the heavens, these crystal spheres, why doesn't the moon fall down on our head? Because it's a heavenly object, it's not a rock.
But the truth is quite different. Not only does the cosmos obey the same physical rules, it is made of the same atoms. The first clue to this came from the Sun. It is 92 million miles away, yet astronomers can tell what it's made of from right here on Earth.
If you take light from some source on Earth and send it through a prism, you see these spectral lines in there which tell you what it's made of. So when this was done with the Sun, they saw these spectral lines of hydrogen. And for the first time ever, did somebody realize that this most central object that everybody before them had seen, was actually made of Earth stuff. That's been a really shocking revelation, which has come gradually, that stuff up there has everything to do with us.
And every star that we analyzed confirmed the same story, no matter how distant. It seemed that the entire universe was made of the same 92 elements.
It's remarkable that the substances which make up ourselves and everything on Earth are, as far as we can tell, identical to what we find in the Sun and in the most distant stars.
So the question was no longer, where did the stuff of our planet come from? But where did the stuff of the universe come from?
We believe everything started off in a so-called Big Bang, a very hot, dense state, nearly 14 billion years ago.
The Big Bang is the cosmologist's story of how everything in the universe was created in a giant explosion. But the early universe contained a far simpler atomic mix than today. In fact, just two elements existed, the simplest atoms imaginable.
If you'd been looking at the universe when it was, say, a few million years old, it would have been a rather boring place. It would have been at about ordinary temperatures, sort of temperature we're at in this room today, but everything in it would have been just a very diffuse uniform gas, nothing else. That gas would have been just the simplest atoms, hydrogen and helium.
But what transformed these two most basic elements, hydrogen and helium, into the 92 elements that make up every galaxy, every star, every planet, and on Earth, everything from crystals to us?
You want to know how, from that simple beginning, everything transformed into the cosmos we see around us today and of which we are a part.
The transformation occurred because simple atomic matter was not all that existed. There was a force, an ever-present fundamental force, that to this day is both familiar and strange.
The main force that changed the universe from being simple and boring to being rich and complex was gravity.
We're used to gravity's effect on Earth, but gravity extends throughout the universe. It keeps the moon in orbit around the Earth, and the Earth tied to the sun. It holds all planets to their stars. It causes stars to cluster in their billions to form galaxies. Wherever in the universe there is matter, gravity tries to draw it together.
The more stuff you have, the more gravity there's going to be. Nobody is above the law of gravity who is made of matter.
And from the beginning, the clouds of hydrogen and helium atoms were subjected to the gentle but ever-present force of gravity. And we see the results wherever we look in the night skies.
Early on, if you had a large cloud of gas, it would exert a very, very large pull on all the gas around it, which would result in the whole thing contracting together and getting smaller and hotter and denser. And gradually this gravitational contraction would overpower the pressure which was trying to blow it apart, to the extent that it would get so hot that you would make a star.
Sometimes people ask, why should we be interested at all in these stars? Stars thousands of light years away, which live out their lives and then die. And the answer is that there's a rather intimate link between these stars and us on Earth. Had it not been for these stars, we wouldn't be here.
Throughout the ages, alchemists, people dreaming of getting rich, were trying to make some elements out of others, typically expensive things like gold out of cheap things like lead, right? And all they achieved typically was lead poisoning. But they weren't actually wrong. We now know it is possible to do alchemy and create new elements out of others. It's just that you need much more energy than those guys had in their makeshift little chemistry labs. You need so much energy that, in fact, only stars can provide them. So stars manufacture atoms in a fusion reaction. The exact same thing that we humans have still failed to do under controlled forms. We can only do it in a hydrogen bomb.
The heat at the core of the first stars began to transform the hydrogen and helium into other atoms.
Early on, when the universe first began to produce stars, started with just hydrogen and helium. And as the stars contracted, the temperature in their cores rose higher and higher, and eventually it began to be possible for hydrogen nuclei to bang into each other and produce helium. And then they contracted further, it got hotter, the helium began to react and produce the other elements that are fairly abundant: carbon, nitrogen, oxygen.
So stars fuse together smaller atoms to make bigger atoms. But how did these larger atoms get from the heart of stars to the Earth?
At certain moments during this process, the stars can become unstable, and then they spew out material. This happens in great explosions, supernova explosions.
And so it is the life and death of stars that have created the 92 elements, the underlying constituents of the universe, of planets, rocks, crystals, water, ants, and us, collected from space, scattered there by exploding stars.
We are literally the ashes of long-dead stars. If you're less romantic, we are the nuclear waste from the fuel that made those stars shine.
Everything we see around us now essentially was made by stars. This is actually something which our grandparents had no idea about. Everything came from stars. In trying to understand our cosmos, we're very much also trying to understand ourselves and how we got here.
Created in the heart of a star and recycled through different forms all over the galaxy, atoms are virtually indestructible.
A single atom, like, say, an atom of carbon, can't be created or destroyed by any process that goes on the Earth. Let's imagine one atom that's in a particular blood cell in my body now. At some stage I probably breathe that in as carbon dioxide in the air. That carbon dioxide might have been put out from a chimney where coal was being burnt. And it would therefore be a relic of some primordial forest maybe 200 million years ago. We can trace it back further to when the Earth first formed. Some earlier star exploded as a supernova and flung out into space the processed debris of the nuclear fuel that kept it shining.
So the scientific quest to discover why we were here had answered at least the more straightforward question, how we were here. Our creation was part of a wider process that happens across space and throughout time, and it seemed to be very deeply ingrained in the laws of the universe. But scientists were soon to discover that a major part of the story of our creation was missing.
We could imagine a universe where there was nothing but atoms, but our universe seems to be rather more complicated than that.
In the search for an answer to the question, why are we here? Scientists had proved that we were made of the very same atoms that made up the entire universe. Over billions of years, the combination of atoms and gravity had created everything. Then out of the blue, we discovered that atoms are not the only ingredient of the cosmos.
When we look at the universe, there's no particular reason to believe we are getting a complete image of what's actually there. We've had some surprises. We've discovered that there's not just atoms, but there's a lot of stuff in the universe which isn't made of atoms at all. Dark matter. The first evidence for dark matter, in fact, goes back to the 1930s, long before I was born.
Galaxies rotate, and at their outer edges, the stars are traveling at phenomenal speeds. The only force holding those outer stars to the rest of the galaxy is the combined gravitational pull of all the atoms in the stars at its center. But when astronomers calculated the amount of gravity required to prevent those stars from flying off into space, they discovered that there simply wasn't enough matter in the galaxy to hold the outer stars in place. Something was very wrong.
By measuring, for example, the speed with which stars go round and round the centers of galaxies, like our own Milky Way, the stars go round too fast. And unless there is some gravitational confining force, some sort of invisible glue keeping the stars together, the galaxies would have just dissolved.
It was already realized then that some clusters of galaxies moving around, would have flown apart had they not been held together by a gravitational pull of something more than we saw. So that was the first intimation of dark matter.
But for many astronomers, the idea that there could exist in our universe a type of matter made from something other than atoms was just too strange to contemplate.
People didn't want to think that the universe was full of dark stuff that we couldn't study. And after all, justifying a huge investment in a telescope requires telling the funding agencies we're going to discover what the universe is made of. People were telling you, look, your telescopes only see a little bit of what is there, are not necessarily popular. So partly for that reason, and partly because there was no theory as to what the dark matter could be, that idea lay dormant. It was a niggling thought in the back of people's minds until the 1970s, when more direct and compelling modern evidence for dark matter was acquired, and then it was just staring us in the face. We couldn't ignore it anymore.
And when they calculated the amount of dark matter in the universe, astronomers were even more surprised. This mysterious material made up the majority of the universe, nearly 85% of it.
The realization that most of the mass in the universe is dark matter has come as a big shock to the community.
And we have no idea what it is.
Unlike ordinary matter that we understand and we know and love, we know how to make it, and we know its composition. We know relatively little about dark matter. The name dark matter just reflects the fact that we're talking about matter that does not emit light or radiation of any sort. We believe that the dark matter is made of elementary particles. These particles, which are still hypothetical, I should say, this is something that has yet to be confirmed in the laboratory, go straight through you, and you're none the wiser. And that makes it very difficult to detect these particles, because the way you detect the particles is by stopping it, intercepting it. But if you just go straight through the detector, then you don't know that there was a particle there. And so they're harmless from that point of view, but they're all over the place. There's billions of these dark matter particles crossing my hand every second as we speak, and you just don't feel it. They don't interact. They just do nothing.
In fact, it'll happily go right through planet Earth and out the other side without even interacting, which makes it feel almost metaphysical. If there's no experiment you can do which will let us capture one of these particles, how do we know that they exist?
The actual nature of the dark matter is a mystery. There are lots of candidates which could exist in the early universe, in the Big Bang, in the first microsecond. And if they are still around now, they would be candidates for the dark matter.
It's sort of a wacky idea. It sounds sort of frivolous to invent something which you can't see, can't touch, to say that it nonetheless exists. So far, we only know that they exist because of the gravitational pull. A very interesting question to me is the universe more complicated than it needs to be to have us here? In other words, is there anything in the universe which is just here to amuse physicists? It's happened again and again that there was something which seemed like it was just a frivolity like that, where later we've realized that, in fact, no, if it weren't for that little thing, we wouldn't be here. I'm not convinced, actually, that we have anything in this universe which is completely unnecessary to life.
Surely this mysterious and abundant matter must have had an effect on the history of the universe. And if so, it must have played an important role in our own creation.
With the power of modern supercomputers, we are now able to replicate cosmic evolution with great precision through simulations. So we are now able to make replicas of the universe in a computer. And this is a very powerful tool that cosmologists have developed in order to understand the universe. If you are able to synthesize cosmic evolution in a computer, you can then play games with the universe. I worked on trying to make universes without dark matter in a computer, and they were always a disaster. They just never worked. So a universe without dark matter is just a failed universe. It's a pretty boring, barren place. Galaxies just don't form, and if galaxies don't form, stars don't form, and if stars don't form, presumably people don't form. It was only when we got the right chemistry, the right mix of dark matter and ordinary matter, that we suddenly came up with replica universes that for all intents and purposes look just like the real thing. The right number of galaxies, the galaxies have the right sizes, they're in the right places. It's beautiful universes.
Without dark matter, we would not be here. How could a cosmic ingredient so fundamental to our own existence have escaped detection for so long?
In my opinion, we should not have been surprised by this. There's no particular reason why everything in the universe should shine. The conspicuous things shine, but much could be dark. If you take a picture of the Earth from space at night, then you get a few cities lit up and oil fields in the Middle East, etc., but you get a very distorted and incomplete picture of what's really there. So I think we shouldn't have been too surprised by the presence of dark matter. It's gratifying to have evidence for it.
If there was no dark matter, then life probably would not exist, because the origin of stars, planets, and people relies on the action of dark matter. Because the dark matter is the engine or the motor that allows complexity to evolve. Even though ordinary matter is a minority in terms of mass and in terms of amount, it's of course where all the excitement is, because that's where stars which shine and planets that are exciting and people come from.
But would this mysterious substance, so vital to our evolution, play a part in our future?
We've achieved amazing success in being able to delineate the structure of the universe as we observe it and what it's made of. It took several hundred years for navigators to explore the Earth and map out the continents and work out the size of the Earth and its shape. In the last 10 or 20 years, we've done something analogous for the vast universe we can observe, a universe extending more than 10 billion light years from us.
Having figured out the role dark matter had played in creating us, the most complex collection of atoms in the universe, cosmologists were keen to see how it might affect our future. And to assess how dark matter might affect the future, scientists had first to peer into the past. Since its beginning in the Big Bang, the universe had been expanding outwards. Intuitively, scientists expected that this expansion would be slowing down.
The amount the expansion is slowing down would be determined by how much gravitating stuff there is, because everything exerts a gravitational pull on everything else, and so the more gravity there is, the more it is slowing down.
If you could find out that it was slowing enough to someday would turn around and come to a halt, then effectively you would have found out that the universe was going to come to an end. And of course, you could find out the opposite, that the universe was slowing, but not enough to ever come to a halt. Then you know that the universe is going to last forever. And I figured, what could be a better project than that, than to measure the fate of the universe?
To study how much the expansion of the universe has slowed, you need to know how fast it was expanding in the past. And peering back in time is not as impossible as it sounds. To look at any star is actually to look back in time. Because although light travels very fast, it still takes time to reach us. Light from our nearest star, the Sun, takes 8 minutes to reach us. But to study the earliest stages of the universe, astronomers had to search out the most distant stars. And the brightest of them are exploding stars.
For decades, astronomers had been fascinated by these exploding stars, the supernova. And I think partly just because people love seeing a really dramatic explosion. These things are so bright that they outshine almost the entire galaxy of stars that they explode in. That's some 10, 100 billion stars. And this one star that explodes is brighter than all the rest, just for the month or so that it's exploding, and it's visible. You can tell then how far away the supernovae are by how bright they got to be.
And the distance tells us how long ago it exploded.
The amazing thing is that by now we've seen supernova explosions which are so faint, so that they're so far away that they represent an explosion that occurred some 10 billion years in the past. And we're just seeing that pulse of light reaching us today that exploded from 10 billion years ago.
The color of the light from these supernovae tells us how fast the universe was expanding at the time they exploded. Because the expansion of the universe affects the color of the light from the supernova.
The supernova, intrinsically, when they explode, are mostly blue. So if you were nearer one of the supernova and survived, what you would see would be mostly a blue explosion. However, while the universe is expanding, the light travels to us from that supernova in an expanding universe, and everything in that universe that's not held together by some force stretches with the universe. And one of the things that stretches with the universe expansion is the very wavelengths of light that are traveling to us from that supernova.
The difference in the detected colors of supernova of different ages tells astronomers exactly how much the expansion of the universe has slowed down. Saul Perlmutter set himself the unlikely task of catching exploding stars.
As they started coming in, the whole group of us, we were all cheering, and we had a party that weekend where we had a bottle of champagne for every one of the supernovae we discovered.
But as the data flowed in, the slowing down effect they expected didn't materialize. In fact, quite the reverse.
After a while, we started realizing there's actually something that's causing the universe to speed up.
Nothing in the history of astronomy had prepared cosmologists for this. In fact, with the avid gravitational braking of dark matter, the acceleration seemed even more paradoxical.
This came out of the blue. This would be something where the universe basically wants to expand faster and faster and faster, and there's something apparently powering that expansion. And this is new. This is not something we've had before in our physics. If you asked the physicists, the theoretical physicists, what could do that, they said, well, if you came up with some way of having an energy of a certain kind that spread out through all of space, then you can actually get that to cause the universe to accelerate faster and faster.
Whereas dark matter shocked scientists by revealing that most of the substance of the universe was invisible, now they had discovered that empty space possessed an inexplicable energy.
If you imagine taking a volume of space, removing from it all the atoms, all the energy, all the magnetic and electric forces, etc., you might think you end up with zero. But it looks as though you don't end up with something which is exactly zero. There is still something there. That something exerts a force which seems to be the opposite of the force exerted by normal gravity. It's a force which seems to cause things to disappear away from each other rather than be attracted towards each other. Why empty space itself should be more than just nothingness and have these complicated properties is indeed a very deep mystery.
They named the source of this mysterious expansion dark energy.
It sounds like you know what it is if you give it a name, if you call it dark energy. But in fact, if you talk to almost any scientist today, they would say they've got no idea what dark energy is.
Cosmologists are also unsure of the role dark energy will play in the future of the universe. It could make the universe expand forever, pushing everything apart to its destruction. What started with a Big Bang may end with a big rip.
In fact, that beneficial building of complexity may have just been the first phase of the universe, and that most of the universe actually will be spent tearing it all apart. And that would be, of course, a rather disappointing conclusion to what looked like a very promising beginning.
Others believe that the local process of building ever more complexity will continue, regardless.
The extra force has no effect here on Earth, nor even in the solar system, nor even in the galaxy. But it comes into its own on the intergalactic scale when the gravitational pull is overwhelmed by a force which is actually pushing things apart rather than pulling them together. And this force is due to the very mysterious dark energy.
Although dark energy is key to understanding our ultimate fate, physicists face a massive challenge to understand it.
You might think that the physicists would have been crestfallen, but in fact, it works exactly the opposite way around. Physicists love a challenge, and I think they love a mystery. And so for them, this was the most exciting, most fun thing that had happened in years.
But for some, the likelihood that we have any role or purpose has been made less likely by the very discovery of the dark side of our universe.
I think the experience of doing science and learning about science leads to a rather melancholy view of man's position in the universe. We're not in any very important place in the universe or in the laws that govern the universe.
Others disagree. Many cosmologists believe we may still have a special place in creation. Whatever part dark matter and dark energy have played up till now, they haven't hindered our evolution. Indeed, we wouldn't be here without them. Perhaps as we come to better understand dark matter and dark energy, we will realize they are not the enemies of the complexity which created us, but vital parts of it. So the question of why we are here is still open.
As we've surveyed the cosmos in more detail and with more precise instruments, we've compiled a more complete inventory of the things in it. When we have a deeper understanding of the basic laws, I suspect that we will think that it is natural that we have these three ingredients, though it looks like an unaesthetic complication at the moment.
In many scientists' minds, it should be much simpler than that. We should be able to come up with a theory that makes sense out of all these things all at one time. Suddenly we'll say, oh, with that fundamental simple principle, it all makes sense. You don't have to have lots of different explanations for different things. It all fits into one big story. That's the aha moment that we're looking for. We want to have that real sense of, that's, that must be the truth.
Maybe a good clue to why dark matter and dark energy are around in the amounts that they are is that if you change greatly the amounts of either one, we wouldn't be here. With no dark matter, our galaxy wouldn't have had enough gravitational material pulling it together to actually form. With the dark energy, it's the opposite. The dark matter is our friend. We need it to form objects. Dark energy is our enemy. If you have too much of it, it just stops things from forming and blows things apart.
There's no particular reason why our human brain should have evolved just far enough to be able to assimilate the deepest levels of reality. What is amazing is that we've been able to make so much sense as we have of the external world. We have pinned down some of the general properties of our universe, just as early navigators pinned down the general configuration of the continents and the size of the Earth. But that was not the end of exploration of the Earth, and likewise we are at the beginning rather than at the end of our exploration of the universe. And I believe when the history of science is written, then what's been discovered about our universe in the last decade or two will be one of the most exciting chapters. But the key question, of course, is what we still don't know, and that is the challenge for the coming century.
More next week, same time. Tomorrow at 8, Respected and Independent. Hang with American filmmaker Richard Linklater in the art show. But next tonight, check out the pom-poms on Kirsten Dunst in the cheerleading film Bring It On.